Welcome to today's paper reading. Today's paper is titled, Instruct-Imagen, Image Generation with Multimodal Instruction. This paper was published on the AR14 preprint by Hexiang Hu and colleagues from Google DeepMind and Google Research. This paper introduces Instruct-Imagen, a model designed to handle diverse and heterogeneous image generation tasks and generalize effectively across previously unseen tasks. The model employs multimodal instructions for image generation, which articulate a range of generation intents with precision. These instructions use natural language to combine various modalities, such as text, edge style, and subject, allowing for a standardized format for numerous generation intents. The development of Instruct-Imagen involves fine-tuning a pre-trained text-to-image diffusion model in 2 stages. Initially, the model is adapted using retrieval-augmented training to enhance its ability to ground its generation on external multimodal contexts. Subsequently, the adapted model is fine-tuned on various image generation tasks requiring vision language understanding, each paired with a multimodal instruction encapsulating the task's essence. Human evaluations on various image generation datasets show that Instruct-Imagen matches or surpasses prior task-specific models in domain, and demonstrates promising generalization to unseen and more complex tasks. The evaluation suite will be made publicly available. Figure 1 illustrates the zero-shot generalization capability of Instruct-Imagen. The model demonstrates its ability to understand multimodal instructions on the left and generate images on the right that reflect complex and previously unseen image transformations. This showcases the model's proficiency in handling diverse and intricate instructions without prior exposure to similar tasks. The introduction of generative artificial intelligence, particularly in text-to-image models, has led to significant advancements. However, existing models like Stable Diffusion and Dream Booth have limitations in handling complex, multimodal instructions. This gap highlights the need for models that can effectively process and generate images based on such instructions. Unlike language generation, image generation inherently involves multiple modalities, as seen in human artistry where various elements like sketches, styles, and subjects are integrated. To address these complexities, the authors introduce multimodal instruction in image generation, which integrates information from different modalities to describe the objective of generating customized images. They then develop Instruct-Imagen, a model employing a 2-stage training approach to enhance the model's ability to process multimodal instructions and faithfully follow user intents. This involves adapting a pre-trained text-to-image model to handle additional multimodal inputs and fine-tuning it to respond accurately to multimodal instructions. Instruct-Imagen demonstrates strong capability in understanding sophisticated multimodal instructions and generating images faithful to human intentions, even for unseen combinations. Human studies show that Instruct-Imagen not only matches but often surpasses prior task-specific models, exhibiting promising generalization capabilities for complex, unseen tasks. This section introduces diffusion models, which are latent variable models parameterized by theta. These models are defined by the integral of the joint distribution over latent variables. The diffusion process involves a predefined Markov chain that adds Gaussian noise to the data according to a schedule beta t. Training these models involves learning to reverse the diffusion process, specifically by denoising xt back to x0, using a time-weighted square error loss. The training dataset D consists of pairs of images and their corresponding conditions. The Instruct-Imagen model is built upon a multimodal instruction framework that allows for a uniform representation of various image generation tasks and the ability to extend to novel and complex tasks. This is achieved through a cascaded diffusion model that is fully conditioned on the input multimodal instruction. The training of Instruct-Imagen is conducted in 2 stages. The first stage focuses on text-to-image generation with augmented data, and the second stage involves fine-tuning on a mixture of diverse image generation tasks paired with multimodal instructions. The model architecture includes a pre-trained Imagen model, which is adapted by introducing a cross-attention layer that conditions the bottleneck representation with embedded multimodal context, resulting in a parameter increase from 2.51 billion to 2.76 billion. Figure 2 illustrates how multimodal instructions can uniformly represent existing image generation tasks and extend to new tasks. The figure showcases examples from 7, 42, 50, demonstrating the format's compatibility with prior image generation tasks. The key components include a payload text instruction with detailed task descriptions and reference markers, and a multimodal context that includes pairs of markers, text, and images. This format allows for a shared model to understand both text instructions and multimodal contexts, regardless of the specific modalities involved, thereby enabling flexibility and generalization to new tasks without task-specific design. Figure 3 provides an overview of the two-stage training pipeline for the Instruct-Imagen model. The first stage involves continuing text-to-image generation with augmentation of retrieved neighbor, image, text pairs. The second stage fine-tunes the output model from the first stage on a mixture of diverse image generation tasks, each paired with corresponding multimodal instructions. The training is optimized end-to-end in both stages. This approach allows the model to learn to condition on multimodal inputs for generation, deviating from standard text-to-image pre-training. The pipeline includes a retrieval-augmented training dataset constructed via domain-specific clustering of web, image, text, pairs, and a multimodal instruction tuning process that prepares diverse image generation datasets for fine-tuning. Table 1 provides a comprehensive overview of the instruction tuning datasets used in the training of the Instruct-Imagen model. It details 11 distinct image generation datasets, categorized into 5 main task groups, each with specific model input conditions and data statistics. The table also outlines the mixing ratio for these datasets, which is crucial for the multitask mixed dataset used in the instruction tuning stage. This information is essential for understanding the diversity and complexity of the data on which the model is fine-tuned, enabling it to handle a wide range of image generation tasks effectively. In the realm of instruction tuning, Flan was the first to introduce the concept, fine-tuning large language models to enhance zero-shot learning. Chang et al. Expanded this work, demonstrating exceptional generalization across various NLP tasks. This success was later applied to vision language models, enabling task generalization in recognition and visual QA. Meanwhile, controlled image synthesis has seen significant advancements with text-to-image models, showcasing impressive capabilities in creativity and photorealism. These models have enhanced controllability through adaptations to specific subjects and styles. However, a common limitation is their specialization in specific modalities, leaving generalization to novel modalities unexplored. To address this, the authors introduce Instruct-Imagen, a novel model designed to understand complex relationships and generalize effectively to unencountered tasks. In this section, we discuss the experimental setup, main results, and model analysis. The experimental setup includes in-domain task evaluation and zero-shot task evaluation, which are more challenging. We compare Instruct-Imagen with various baseline models. The main results show that Instruct-Imagen achieves superior performance, especially in tasks with limited training data, without requiring fine-tuning. Additionally, we perform a model analysis to explore the adaptability of Instruct-Imagen to new tasks through fine-tuning and the impact of retrieval-augmented training. We also identify common failure modes of the model. Figure 4 presents the results of a human study comparing Instruct-Imagen with prior methods and baseline systems. The study reveals that Instruct-Imagen performs on par or better than the baselines and prior methods, demonstrating superior generalization capability to novel tasks. Notably, Instruct-Imagen does not require any fine-tuning for tasks related to style or subject, and it achieves an average inference speed of 18.2 seconds per example when running on TPU v4. Figure 5 presents a comparison of in-domain tasks, showcasing examples generated by prior methods, baselines, and Instruct-Imagen. The figure visualizes multimodal instructions to aid human intuitive understanding. These models are evaluated using in-distribution inputs, highlighting the performance differences across various methods. Table 2 presents the evaluation results of masked image editing on the Imagen Hub benchmark. It compares the performance of Instruct-Imagen with various baseline models, focusing on human score and accuracy metrics. The table highlights the improvements achieved by fine-tuned Instruct-Imagen, demonstrating its superior performance in image editing tasks. Table 3 presents an ablation study on the impact of retrieval-augmented training on model performance. The study reports average in-domain and zero-shot evaluation scores, showing that retrieval-augmented training significantly enhances both in-domain and zero-shot performance. Specifically, without retrieval-augmented training, the in-domain score is 0.55 and the zero-shot score is 0.53. With retrieval-augmented training, these scores improve to 0.79 and 0.59, respectively, demonstrating the importance of this training method for handling multimodal contexts effectively. Figure 6 presents a comparison of zero-shot task examples generated by prior methods, the baseline, and Instruct-Imagen. The figure visually represents multimodal instructions to aid human understanding, with models evaluated using in-distribution inputs. This comparison highlights Instruct-Imagen's superior performance in instruction following and output quality, especially in scenarios involving multiple references in a multimodal context. Figure 9 presents an additional qualitative evaluation of Instruct-Imagen focusing on control plus style generation. This evaluation aims to assess the model's capability in generating images based on unseen, diverse, and sophisticated multimodal instructions. The results highlight the model's performance in maintaining control and style consistency across various image generations. Figure 10 presents additional qualitative evaluations of Instruct-Imagen's performance on multi-subject generation tasks. The figure showcases the model's ability to handle diverse and sophisticated multimodal instructions, using images that were not part of the model's training data. This evaluation aims to explore the limits of Instruct-Imagen in generating high-quality, multi-subject visual content based on complex instructions. Figure 11 presents an additional qualitative evaluation of the Instruct-Imagen model, focusing on its performance in control plus subject generation tasks. This evaluation aims to provide insights into the model's ability to generate images based on specified controls and subjects, showcasing its capabilities in handling complex visual generative tasks. Figure 12 presents additional qualitative evaluations of the Instruct-Imagen model focusing on styled subject generation. This evaluation showcases the model's capability to generate images of subjects in various artistic styles, demonstrating its effectiveness in comprehending and executing complex visual instructions. The figure highlights the model's performance in generating styled images, which is crucial for tasks requiring artistic or thematic consistency in image output. Thank you for watching.